Kajrare, tere kale kale na. Let's start, guys. Let's start. Hey, everybody. We're live and in stereo. We're going to do the 2024 theory set for Equilibria. Sir, where can I find these questions? Oh my God, kill me, please. This is my own topical booklet. You can purchase it from by contacting the number provided behind the topical booklet in every single video on my Instagram at carboxylchem. You could find it. And yes, I've shared it a billion times in the group, but yeah, you could get this stuff, right? Now it says define Le-Chatelier's principle, right? And we are going to define it the way our syllabus requires us to define it, right? So that's the first part. And see, it's 2 marks, free marks, right? What's Le-Chatelier's principle? He says, hey, if a change is made to a system at equilibrium, what would happen? What would happen, sir? At dynamic equilibrium, it's better. Yes, that's how it's written. You're right. At dynamic equilibrium, what would happen? The position of the equilibrium would move to minimize that change, right? So the position of equilibrium would move, moves to minimize that change. Moves to minimize this change that you made, right? That's how our syllabus defines it, and that's how I'll define it. Reaction 1 describes the reversible reaction between yellow Fe3 plus ions and colorless SCN minus ions, right? To produce FeSCN2 plus. Now, what is SCN called and what is FeSCN2? Well, I couldn't care less, right? Now it says reaction 1. You have yellow Fe3 plus ions, you have colorless SCN minus ions, and you have red solution right here because of Fe being bonded right here, okay? And the enthalpy change is negative. So it's negative X, that means the forward reaction is exo and the reverse reaction is endo, right? Whenever you give an enthalpy change, unless and until they specifically say that it's for the reverse reaction, they always talk about the forward reaction. So that's minus X, which means this is exo and that's endo, right? Now it says a mixture of Fe3 plus aqueous, SCN minus aqueous, and FeSCN2 plus aqueous is at equilibrium at 20 degrees Celsius. The temperature of the mixture is then increased to 50 degrees Celsius, right? Now, I'll stop here for a moment. If you increase the temperature, increase in temperature according to Le-Chatelier's principle favors what? Increase in temperature favors endothermic, because you want to absorb that extra heat. The system wants to minimize this change by absorbing the heat, right? And therefore it favors bond breaking, which is endothermic, right? And endothermic is the forward reaction or the reverse reaction, which is obviously the reverse reaction, right? Endothermic is the reverse reaction right here. So what should happen to the colors in this entire mixture? It should be more yellow or paler red, right? More yellow or paler red. That's what should happen, right? So this is something that you should be very familiar with, and it's basic O-level IGCSE knowledge, not even A-level knowledge, right? So, and I've taught this in this chapter, by the way. Deduce the color changes that occur, if any, in the equilibrium mixture at 50 degrees Celsius compared to the equilibrium mixture at 20 degrees Celsius. So what's the color change? So we know at 50, you're going to have a more yellow color or a paler red color, however however you want to write it, or you would say more orange as well. It doesn't really matter. So the change in appearance is it's more yellow at 50 degrees Celsius, right? Please note that if I were you in the exam, I would write these proper phrases, right? Instead of saying it's more yellow, I want to tell the examiner that, let me tell you, it's more yellow at 50. I know it's more yellow at 50. I won't just write it's more yellow, because you never know with the examiner. Maybe he says, okay, it's fine because I've written 50 degree and 20 degree here, so I want you to compare this with this with this. But if he wrote it oppositely and you were to compare 50 with 20 instead of 20 with 50, your answer would still be correct if you were to specify what you're talking about, right? Change in relative concentration of this fella right here. What's the change in concentration? Well, we understand that if I increase the temperature, it favors endothermic, which is the reverse reaction, and therefore the equilibrium position shifts to the left-hand side. The position of the equilibrium shifts to the left-hand side, and you make more reactants, don't you? So what should happen to the concentration of FeSCN2 plus? It decreases. So the change in relative conc of FeSCN2 plus is that it decreases. And I could just even write it decreases because I swear to God, I just couldn't care less. Change in the value of Kc. And this is something I've taught you, and voila, it's tested in the 2024 exam. And before this, I don't think it was tested with such a beautiful, beautiful idea, right? So before it was just, hey, does temperature affect it? Yes, it does. Yes, it does. Yes, it does. But now we know that yes, temperature indeed affects the Kc values. And how will it affect the Kc value? Would it increase it or decrease it? Would it lower it or increase it? What would happen? Well, we know Kc values is basically what? It's literally a ratio of products to reactants. And we studied this in the last class, right? So if the equilibrium shifts to the left-hand side, what's happening to the products, right? It's basically FeSCN2 plus concentration of this divided by concentration of this times concentration of this at equilibrium, right? So if the equilibrium shifts to the left-hand side, this automatically decreases. The numerator decreases. And so what should happen to the Kc value? It should therefore decrease. Decreases, or it's lowered, whatever one, however one you want to write it. That's it. And it just says deduce it. Don't describe it or explain it. Just tell me, is it decreasing or increasing, and that's it. I'll give you the mark for it. In another experiment, equimolar amounts of Fe3 plus aqueous and SCN minus aqueous are mixed together and allowed to reach equilibrium. The total volume of the mixture is 25 cm cube. That's very important. He's given me the volume, right? Okay, great stuff. Now he's giving me this reaction one. He's saying at equilibrium, a mixture contains this fella and this fella. And it says calculate the initial amount in moles of Fe3 plus aqueous added to SCN aqueous to produce this mixture. See, initial moles. Let's use our ice tables. That's it. This is what we have been prepping for since day one. So I have Fe3 plus SCN minus, Fe3 plus SCN minus. What else? FeSCN2 plus, FeSCN2 plus, right? So ice tables. Initial moles. Do I have the initial moles? No, I'm given equilibrium stuff, but I'm not given initial moles, right? So the initial moles for iron 3 plus X, I don't know. And because, he's saying I'm adding equimolar, which means the same number of moles, right? Equimolar means same number of moles of Fe3 plus are being added to SCN minus. So if this is X, this should also be X. And initially you have 0 products. We all know that. Good stuff, great stuff. Now at equilibrium, what are the moles at equilibrium, right? Should I just write 1.3 here, right? Should I just write 1.3 here? The SCN minus and this right here. Should I write 1.3 into 10 raised to the power minus 3 here? And should I write 0.3 into 10 raised to the power minus 3 here? And the answer is no. Although your examiner has used this shortcut, and this is what I wanted to see. I looked at this, and although you can use this shortcut, but I would never recommend to use these pathetic and fazul kisam ke shortcuts, because there are a couple of assumptions related to it. So I would never ask you guys to use it, and I would discourage using these shortcuts. And if somebody wants to know the reason for it, I'll tell you later on. But we know that these ice tables are for moles, right? So these are the initial moles, this is the change in moles, and these are the moles at equilibrium. Sir, I'm not given the moles at equilibrium. I'm given the concentration at equilibrium, but I'm also given the volume. So I can use this volume and concentration to figure out the moles at equilibrium, can't I? So instead of writing this right here, I'm gonna erase it. I'm going to say, hey, let's figure out the moles at equilibrium of SCN minus and FeSCN2 plus, right? Because we want a very systematic way to solve questions. Either shortcut lag gaya, udhar lag gaya, pathetic. Right? And I wanted to check whether they've acknowledged this. So N is equal to Cv. Moles I need to figure out of SCN. Concentration at equilibrium is 1.3 into 10 raised to the power minus 3. Right? And volume is what? 25 cm cube converted into dm cube. So 25 times 10 raised to the power minus 3. Right? 25 divided by 1000 or 25 into 10 raised to the power minus 3. You should now be clearly comfortable with these minus 3s and whatever. So what do you get? How many moles do I get, sir? How many moles do I get? Help me out, please. Help me out. How many moles do I get at equilibrium? Right? I'll do it for FeSCN2 plus as well. So N equals Cv. Somebody calculate it and tell me. Moles I need to find. Concentration is given to me. It's 0.3 into 10 to the power minus 3. 0.3 into 10 to the power minus 3. That's the concentration. What's the volume? 25 into 10 raised to the power minus 3. How many moles am I getting for both? Help me out, please. 7.5 into 10 raised to the power what? Minus 6. Sure? Minus 6. Okay. So I'm getting the moles at equilibrium for this fella right here is 7.5 into 10 raised to the power minus 6. Right? And what are the moles for this fella? SCN minus at equilibrium. Hanji, help me out. 3.25 into 10 raised to the power minus 5. Okay. So 3.25 into 10 raised to the power minus 5. Thank you. Hamza is saying minus 6. One is saying minus 5. One is saying minus 6. Please use the calculator. I can't teach you guys how to use the calculator. Please. Like if you make these silly mistakes, is it minus 6 or minus 5? Acha. Hamza is saying 32 point. Hamza, please tell me in terms of 3.25 into 10 raised to the power minus 5. Okay. 3.25 into 10 raised to the power minus 5. Now is where the fun stuff starts, right? Now please understand, what are the moles at equilibrium for FeCN2+, right? What are the moles at equilibrium? We have this. And initially you had 0, right? Initially you had 0, and at equilibrium you have these many moles. What's the change in moles? What's the change in moles? Plus 7.5 into 10 raised to the power minus 6. That's the change in moles. And now you can use this entire row to actually figure out these changes, because they're all in 1:1:1, right? So what's the change in moles? This should be minus 7.5 into 10 raised to the power minus 6. This should be minus 7.5 into 10 raised to the power minus 6. And we are concerned about what? We are concerned about the initial moles of Fe3+, right? So if I just calculate this fella, I will actually even figure out the moles of Fe3+. How? Sir, I know x minus 7.5 into 10 raised to the power minus 6 should give me 3.25 into 10 raised to the power minus 5, right? And what do you get? X equals, add them together, what do you get, sir? 4.0 into 10 raised to the power minus 5. See? So this is the value of x, 4.0 into 10 raised to the power minus 5. And this is the value, the initial moles of Fe3+, 4.0 into 10 raised to the power minus 5, right? And then you could even subtract this from it to figure out the moles at equilibrium for Fe3+, which would be the same, which would be literally the same, right? You could figure this stuff out, or you could say, hey, the moles at equilibrium for this and this are the same because they are equimolar. So this would also be 3.25 into 10 raised to the power minus 5. Again, same thing, same idea. So that's the answer. That's it. How easy. How easy. So just need to be very careful. If you're given concentrations, convert it into moles first, please, because ice tables are for moles. I don't want you guys using shortcuts, because if you use shortcuts, I have no problem with it, but you'll get stuck later on in the future. So it's up to you. Those who want to know shortcuts, I'll teach it 5-10 days before the exams. It's just, instead of using moles, the examiner basically uses concentrations, and then when he figures out I is also in the form of concentration, and then he converts this concentration into moles again. So it's the same idea. Either convert these concentrations at equilibrium into moles and figure out the moles initially, or you have concentrations at equilibrium, figure out the initial concentrations, and then convert it back into moles. But I recommend this way, systematic. Done, guys? Piece of cake. Sir, please look at my answer for and Usa. Yeah, it's equimolar trimer. That means both are x and x, both moles same, right? So what's the the initial amount? It's 4.0 into 10 raised to the power minus 5. Easy peasy, a lemon as squeezy. Now, calculate Kc for reaction 1 and state its units. So how do you calculate Kc? Kc equals the concentration of FeSCN2+ at equilibrium divided by the concentration of Fe3+ and SCN-. So concentration of Fe3+ and SCN- at equilibrium. So how do you calculate Kc? Sir, what's the concentration of FeSCN2+? That is 0.3 into 10 raised to the power minus 3. See, these are concentrations now. 0.3 into 10 raised to the power minus 3. That's the concentration at equilibrium divided by 1.3 into 10 raised to the power minus 3. 1.3 into 10 raised to the power minus 3 at equilibrium, right? And because they were equimolar, you could say, hey, the concentration of Fe3 plus is the same, 1.3 into 10 raised to the power minus 3. But if you really want to calculate it, you can. See, you are given the moles here at equilibrium and then convert it into volume. Take these moles at equilibrium and convert it into concentration, by dividing it by volume. So take 3.25 into 10 raised to the power minus 5 divided by 25 into 10 raised to the power minus 3, and you're going to get the same concentration as the SCN minus I, right? So what do we get? Piece of cake. What do you get? Somebody calculate it for me. 1.7751. Okay. Now the question is, sir, how many decimal points should I write my answer to? Please understand that, see, if you look at your questions, even you could have written this as 4.00 into 10 raised to the power minus 5. That wouldn't make a difference. But if you look at your question, see, the question gives you answer. Look at this. The question gives you data correct to 3 significant figures. See, 1, 2, 3. 1, 2, 3. 1. No, this is not a significant figure, sorry. 1, 2, 3. 3 significant figures are given to me. So what should my answer be? And should it be 177.5? The examiner will deduct a mark. Right? What should it be? It should be 178. So always write the answer in the as per the number of significant figures given in the exams. This you could have also written 4.00, but okay, the exam's like, okay, just cut me some slack. And what's the units for it? Sir, you know that in the numerator, I'll call concentration as M. So M is the concentration for the numerator, and you have M squared in the denominator. What do you get? M minus 1. And M is equal to mole per dm cube, right? So mole per dm cube raised to the power minus 1. What do you get? Mole minus 1 and dm cube. This is the unit. Mole minus 1 dm cube. Piece of cake questions. Describe what is meant by dynamic equilibrium. Well, in an isolated system where the rate of forward reaction, when the rate of forward reaction becomes equal to the rate of reverse reaction, is equal to the rate of reverse reaction, and the concentration of reactants and products no longer changes. Are they equal, or do they just no longer change? No longer changes, or is constant. Not equal, not necessarily equal, but no longer changes. And this is in an isolated, or instead of isolated, let's use the word of the books, in a closed system. Done. Next. Reaction 4 describes the reversible reaction, and it's a different question, by the way. So it describes the reversible reaction between yellow Fe3 plus aqueous and colorless SCN minus aqueous to produce red, this fellow. Okay, great. An equilibrium mixture contains Fe3 plus aqueous, blah, 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 a few colorless crystals of soluble. Soluble means it dissolves. Dissolves means you're going to get K plus ion and SCN minus ion, right? So he's saying a few soluble crystals of K SCN are added. Great. He's saying the mixture is left. Now, wait a moment. It was at equilibrium. He's saying an equilibrium mixture. This was already at equilibrium, and now you made a change to the condition. What does Lee Shortley says? The system will counteract as to minimize the change, right? So what you've done is you've added more SCN minus ions. You've added SCN minus ions more and more and more. So what you've done is you've increased this fella right here. What would the system want to do? The system will want to decrease it by making more products, by shifting the equilibrium to the right hand side. Right? So equilibrium shifts to the right hand side. Because you made this change, you increased SCN minus, the system will want to decrease. It's counteracted to minimize this increase that you've made, to minimize this change by making more products, and thus the equilibrium position would shift to the right hand side, and you're going to be more red, right? So, or paler yellow. Deduce the changes that would occur if this is added compared to the original equilibrium. So compared to the original equilibrium, you're going to have a more red color. Done? And it's saying, what's the relative change in relative concentration of Fe3 plus? See, what's the change in Fe3 plus's concentration? If the equilibrium shifts to the right hand side and it makes more products, Fe3 plus concentration should fall, right? That's just basic stuff, right? So what should happen to the relative concentration? It decreases. Relative means with previous one, right? It decreases, right? decreases. That's it. And he's saying, what is the change in value of the Kc? The equilibrium constant Kc. What's the change in value for the equilibrium constant? Anybody? What's the change in value? There's no change, you dumbo jumbo. No change whatsoever, because we know Kc values are only affected by temperature. There is no change as far as concentration, pressure, catalyst, anything else is concerned, because it's only temperature that dictates this Kc value, that changes it, because it changes the entire energy profile of the reaction, right? It changes the kinetic energies of the molecules. So yeah, and I've proven it to you guys through the reaction quotient, which wasn't a part of your course directly, but reaction quotient was something very interesting. It'll help you out in your MD-Cat and whatever, if you're prepping for bio, for medical and whatever, right? So there's no change, or you could say it remains the same, and whatever. Just try to communicate to the examiner that it remains the same. The expression for the equilibrium Kc for reaction 4 is shown. Thank you very much for showing the expression. I couldn't figure it out on my own. Thank you. Now I think 5 into 10 to the power minus 5 moles of Fe3 plus aqueous and these many moles of SCN minus aqueous are added together and allowed to reach equilibrium. The total volume is this much, okay? At equilibrium, the concentration of FeSCN blah 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 is this much. Calculate the Kc for reaction 4, and it's a piece of cake, right? It's a piece of cake. I just use my ice tables. Remember, I need moles in my ice table, right? So this is Fe3 plus SCN minus, right? And you get FeSCN2 plus. FeSCN2 plus. That's it, a piece of cake. Initial moles of Fe3 plus is 5 into 10 is power minus 3. For SCN minus is 5 into 10. Oh, sorry, not minus 3, minus 5. My bad. This is minus 5. And this is also 5 into 10 is power minus 5. Initially, this is 0. And then he's given you the final. And please, the examiner has lost his or her mind. The examiner has now completely lost it in 2024 or 2023 because they now don't know what to test. Students are just too good at it, right? Or maybe the teachers are too good at it, like Seth Suleiman, oh my god, let's go, right? So they're like, yeah, what should I test now? They all know these ice tables and Seth Suleiman has taught them everything. What should I test? I should just confuse them and, I should just play a game of psychology where students would think, hey, the moles at equilibrium are 4.23 into 10 is power minus 4, but they're my students, you dumb examiner. My students are not this dumb to think that. Why? They're not dumbo jumbos. Why? How does the examiner know? Because he's giving you concentration. Please understand, this is concentration, and we need, for our ice tables, I need the moles at equilibrium. So this is concentration. I need moles at equilibrium. How can I go from concentration to moles? This is the only thing now that the examiner is doing, which is pathetic, frankly speaking. Make good questions, instead of testing psychology here. So moles, concentration is 4 points. So those who quickly read the question and don't see the units with it, you are cooked, guys. So 4.23 into 10 is power minus 4 times by volume. What is volume? He's given me the volume of the mixture, 25 cm cube, convert it into dm cube. That's the only thing he's testing me on. Pathetic. What's the answer, guys? What's the answer? Somebody help me out. Tujhko chaha. Should I do it on my own or can somebody help me out? 1.0575 into 10 is power minus 5. So these are the moles at equilibrium. 1.0575 into 10 is power minus 5. Thank you. And so this is the change, right? So this is the change. Initially they were 0 and now that's the change. And because they're all in 1:1:1, this is positive and all of them are negative. Right? So 1.0575 into 10 is power minus 5 minus 1.0575 into 10 is power minus 5. What do you get, sir? Calculate the moles at equilibrium. Yes, help me out. I get 3.9425 into 10 raised to the power minus 5. 3.9425 into 10 raised to the power minus 5. Done? So these are the moles at equilibrium, please. And what does he want? He wants the Kc values, the Kc value. What's the Kc value? He's already written the expression for me. These brackets also tell you that it's the conc at equilibrium, concentration at equilibrium of this fella, concentration at equilibrium. And he's given me the concentration at equilibrium right here, 4.23 into 10 raised to the power minus 4. right? That's the concentration, raised to the power 1, obviously, nothing. And then what's the concentration of the other two fellas at equilibrium? See, concentration at equilibrium, concentration at equilibrium. You don't have concentration at equilibrium, you have moles at equilibrium. I can just figure out one concentration at equilibrium, and that'll be the same for this, because they are both the same number of moles at equilibrium. So let's just figure this out. N equals CV. Moles, I have 3.9425 into 10 raised to the power minus 5 equals concentration into volume, which is what? 25 into 10 raised to the power minus 3. What do you get as concentration? 3.9425 into 10 to the power minus 5 divided by 25 into 10 raised to the power minus 3. What do you get conc as? Help me out, guys. 1.577 into 10 raised to the power minus 3. That's the conc. That's it. And this will be the same for this fella as well, right? They have the same moles. If you do it, if you want to do it for this fella and waste time, you can do it. It's the same, right? So it's 1.577 into 10 raised to the power minus 3. I hope you guys are giving me the right values, guys. I can only do so much, right? What do you get for your Kc value? What do you get for your Kc value? 170.084 or 9.9 or 4, whatever, right? You guys calculated this stuff. Now he's saying what's the value for it? Now again, before writing the final answer, I'm going to check something. What am I going to check? Let's check how many significant figures are given to me. 1 2 3 1 2 3 1 2 3. So 3 significant, see, 1, 2, 3. 3 sig figs are given to me. So if I just leave my answer like this, it's pathetic. I should write it to 3 sig figs, which is what? 170. And what's the unit for it? See, this is, the unit here is what? It's m, and at the bottom it's m squared, right? M into m. And so what do you get? M minus 1. And m represents mole per dm cube. So mole per dm cube raised to the power minus 1. What do you get? Mole minus 1 dm cube, right? Basically, when you inverse this, mole is raised to the power minus 1. Is simple indices and surds. And dm cube, dm minus 3 is multiplied with minus 1. So you get plus 3 right here. Done. Easy stuff. इसमें कुछ मुश्किल लग रहा है. I don't think it's like a piece of cake. And these are 2024 questions, by the way, which are considered as one of the most difficult questions tested. I don't know what's difficult about this. Done? Okay. N2 gas reacts with H2 gas in Haber process as shown in reaction 1. Table 2.1 shows the different conditions used to produce 3 equilibrium mixtures, A, B, C. Okay, great. Now I think describe and explain the change, if any, to the percentage yield of ammonia produced in B compared to A. Describe and explain the change. So I'm going to look at B and I want to compare it to A. What's the difference in the percentage yield? Let's check out the differences between B and A. See, this is how you need to go over such questions. Don't be scared. Just read the question saying describe if there are any changes in the percentage yield from B to A. Let's first check out what's the difference between B and A. The ratios are same, the temperature is the same, the pressure is the same, the iron presence is, in B you have a catalyst, in A you don't have a catalyst. Oh, you dumbo, catalyst does not dictate the position of the equilibrium, right? You know that this is a negative, it's given to you that the enthalpy change is negative, so the forward is exo and the reverse is endo. But you dumb examiner, you know the catalyst has nothing to do with the position of the equilibrium and therefore the yield, right? It does not affect the position of the equilibrium. So the yield of ammonia is going to be the same, 58%. You dumb examiner, it'll be 58%, same. Why? Because iron is a catalyst and thus does not affect the yield. And you could even tell the examiner, oh, examiner, it affects the rate of reaction. You know? Done. Yeah. So, Rama, they did not ask you about slow reaction or fast reaction. They said what? See, that's the problem. You need to check out the percentage yield, kiddo. The percentage yield. He did not ask you to tell him about rate of reaction. That's just a cherry on top that I wrote, But what happens to the percentage yield? It'll be the same. Right? The percent, or if you want to write better phrases, you can. Describe and explain the change, if any, to the percentage yield of ammonia produced in C compared to A. C compared to A. So now I'm going to compare C and A. What's the differences between the two? If you check this out, they have the same molar ratios. Great. Temperature is doubled here. It's higher. Pressure, same. No. 58, why? Right? So what's going to be the percentage yield? Would it increase or decrease? And so if you've doubled the temperature for C to A, C versus A, you've doubled the temperature, you've increased the temperature. You tell me, increase in temperature, increase in temperature favors what? Favors endothermic, right? As per Lee-Chatelier's principle, it favors the endothermic reaction. And therefore, which is, the endothermic is which side? Left side or right hand side? The forward or the reverse? It's the reverse reaction, which is the reverse reaction, and thus position or equilibrium shifts or moves to the left hand side, decreasing the yield of ammonia in C compared to A. Done. You have to write these things for even a single mark. It's important to tell the examiner you know all of this stuff. Describe and explain the change to the rate. Now he's not talking about the percentage yield anymore. He's talking about the rate of forward reaction that occurs to establish the equilibrium in C to A. So C compared to A. What would happen from C to A? You know that C has a higher temperature, right? And higher temperature means faster rate of reaction. You've studied this in O-level in IGCSE, and you'll study it in chapter 10 as well. You'll recall it, but if you have, that's why I've added this question here, because you've already done it in O-level IGCSE, which is what? Which is that increase in temperature, and that's why I think you do not need to refer to this particular thing. You learned this in chapter 10, what Boltzmann distribution curve is. But see, he said you do not need to refer to it, and that's the reason why I added this question here, because it's basic. Increase in temperature increases kinetic energy of particles, and therefore what happens? Sir, particles, what happens? Sir, rate of reaction increases as frequency of collisions, of successful collisions or effective collisions increases, right? So I've told him, hey, rate of reaction increases as frequency of successful collisions increases. And fun fact, you've also studied the idea that, hey, increase in temperature means that more particles will now have energy. More particles have energy equal to or greater than the EA, the activation energy, have energy equal to or greater than the EA. So more successful collisions, and therefore higher rate of reaction. You've studied this stuff in O-level IGCSE. It's okay, you'll recap it in chapter 10. If you can't, revolve your head around this, it's fine. You'll recap it in chapter 10 again. Write the KP expression for reaction 1. Reaction 1 is what? This N2 plus 3H2 gives me 2NH3. So N2 plus 3H2 gives me 2NH3. Right? What's the KP1? Products over reactants. NH, and we write a slanted P with it. So P NH3, and this is what? Squared divided by, raised to its coefficients, right? Divided by P slanted P N2 right here, and then slanted P H2 and cubed. That's it. What are the units? See, it's P. And please understand that it can be atmospheres, pascals, kilopascals. I swear to God, it doesn't make a difference. But if you write it in atmospheres here, you will get a mark deducted. Why? Because the examiner, when he was talking about pressure, he was giving you atmosphere. So, sorry, if you write pascals below, you'll get your mark deducted, because you also have to see whether the examiner has specified, the units somewhere in the question. These are all the tips that I'm giving you for theory paper. It seems very easy, but students make these silly mistakes and lose a lot of marks, right? So see, pressure in atmospheres. So you can't write it in pascals now. He's already given you the units. So this is what? Atmosphere squared divided by atmosphere to the power of 4. Why? Because it's 3 plus 1, 4, right? So what do you get? ATM minus 2, right? Because this 2 cuts out with this. You get 2 here, and then you just inverse it. So 1 over ATM squared is ATM minus 2. That's the units. ATM minus 2. So the expression and the units. Here you go, examiner. This is working. Equilibrium mixture D is made of 1 mole of nitrogen, 3 moles of hydrogen, and are added in a sealed container. This mixture contains and are left to reach equilibrium. This mixture contains, calculate the mole fraction. We all know what mole fraction is, right? We know it. It's basically the mole fraction of NH3 in D. Mole fraction is what? The moles of NH3 divided by the total moles at equilibrium. That's what mole fraction is, right? The moles of a particular chemical or a particular substance divided by the total moles, and this is obviously at equilibrium. In D is equilibrium mixture, so he's talking about equilibrium. Let's figure it out. Ice tables. It's a piece of cake. If you know your ice tables, it's a piece of cake. Again, N2 plus H2 gives me NH3. So this ice table has made things so much easier. I'm glad, kiddo, I'm glad. 3 plus 2 NH3. Done. Achha, initial moles he's given to you. See, these are the initial moles. Equilibrium mixture D is made when this moles and this moles are added. So these are the initial moles. He's adding them. So it's 1 mole of N2 and 3 moles of this fella. And how many moles of NH3 do you have? Initially 0. But he's saying once equilibrium is reached, you have 1.16 moles of NH3. So at equilibrium, you have 1.16 moles. They're all moles, so it's good stuff. And I know initially you had 0, so 1.16 moles increase happened, right? And see, it's 2 ratio 1. So I know I can now use this entire row to my advantage. I'll say, hey, you went from 2 moles to 1 moles right here. So N2 is going to be half of this change, right? So whatever change you have here, N2 is going to be half of that. Right? See, 1 gives you 2. Right? It's double. NH3 would be double the change, right? So this N2 would be half this change. So 1.16 divided by 2, what do you get? 1.16 divided by 2. See, 1.16 divided by 2. What do you get? 0.58 if I'm not wrong. And this is negative 0.58, right? And see, now this is 1 ratio 3. 1 ratio 3. If you are good in math, you could directly compare these ratios to each other as well, right? I'm not going to do that. You could divide both by 2, and then you could say, hey, 1 gives me 1.5. 1 gives me 1.5. So this times it by 1.5, right? Or you could just say, hey, this is 1, and now this 1 gives me 3. 1 reacts with 3. So this would react. If this much is being used up, 3 of this should be used up. So times it by 3. What do you get? Minus 0.58 times by 3. What do you get? Minus 1.74. Now, moles at equilibrium. Hydrogen ki moles at equilibrium. Nitrogen, if I'm not wrong, is 0.42. And hydrogen is what? 3 minus 1.74. 1.26. Right? What's the moles? The total number of moles at equilibrium? 0.42 plus 1.26 plus 1.16, 2.84. These are the total moles. Thank you. And so now that I have the total moles, what am I going to do? I can calculate the mole fraction of NH3. I had the moles at equilibrium, which is 1.16, divided by the total moles, which is what? 2.84. What do you get as your mole fraction? 1.16 divided by 2.84. You get 0.40845. But then again, look at how the examiner has given me values. He's given me 2 sig fig, 2 sig fig, 2 sig fig, right? Everywhere 2 sig. And then, hey, he's given me 3 sig fig here. Now, this is where your concepts come into play. Remember, he's given me three significant figures here, but he's given me 2 significant figures and 2 significant figures here. And I know we use the lower significant figures. I've given the entire explanation as to why we use the lower number of significant figures, because how can your value be accurate to 3 significant figures if your initial measurement is less accurate? It's only till 2 significant figures, right? So the final value that I'm going to get is not going to be till 3 significant figures. I'll write it till 2 significant figures. So it's going to be 0.41. Done. So not 2 dp. It doesn't have to do with any dp's. It has to do with significant figures. Done. That's it. That's mole fraction. Part moles divided by whole total moles. The mole fraction of N2 is 0.625 in U equilibrium. Great stuff. Calculate the partial pressure of N2. Partial pressure is a piece of cake. Partial pressure of N2 is what? The mole fraction that you have times it by the total pressure. This is how we used to do it, right? If I recall it for you, see, you used to do, hey, these are the moles of N2, these are the moles of N2 present, and the total moles are present. These are the total moles present, and then times it by the total pressure, which is what? 1,000 atmospheres, right? This is how we used to do it. Now he's saying, hey, I'm going to give you the mole fraction. This particular bit is called mole fraction, right? So he's already given it to you. It's 0.625. And so you just have to times it by 1,000. That's it. That's a piece of cake. 625 atmospheres. That's how easy it is, man. I swear to God. Okay. Next. The Haber process involves the reaction of N2 and H2 to form ammonia. A catalyst is used which allows this. The enthalpy change for the reaction is negative 92, right? Now I think use the information and complete the tables. Now because I have taught chemical energetics before this, I have added such questions again here in this chapter. So my questions repeat based on the chapters that I have taught. And this is how you're going to get a clear sense as to how questions are properly tested in the exam. So what is the enthalpy change of formation? It's for 1 mole of this substance forming, 1 mole of this forming, 1 mole of this forming, right? And how does it form? You have elements, right? Right here. And it's 1 mole of this will form, 1 mole of this will form, 1 mole of this is going to form, right? So this is how we calculate the enthalpy change of formation, don't we? Now the question is, sir, what's the enthalpy change of formation of nitrogen? What's the enthalpy change of formation of nitrogen? Sir, it's a null reaction, it's 0. It's an element. Again, if you still make this mistake, please revise chapter 7. 0. Enthalpy change of elements are 0, 0. So this is 0, this is 0. Right? And NH3, you have to find the enthalpy change for NH3. Let's suppose I call this X. Right? I don't know what the enthalpy change here is. I just call it X. Can I use my Hess's law, Hess cycle? See, the indirect root equals the direct root. So can I say, hey, 0 plus minus 92. It's the law of summation. Please do not write 0 minus 92 or do not write minus 92. It's law of summation. You sum. It's all sum. Right? That's why I'm writing minus 92 in brackets. Equals X, right? X equals minus 92. But please understand, this X that you've calculated, this is when 2 moles of NH3 form. 2 moles. Delta H formation is for 1 mole of NH3 forming. So I'm just going to divide it by 2. X is equal to minus 92 divided by 2. It's minus 46. And here you go. Piece of cake, huh? Explain how the presence of a catalyst affects the reaction. How does a catalyst affect a reaction? It increases the rate of reaction. By what? By providing an alternate pathway with a lower activation energy. With lower EA. Done. State and explain the effect, if any, on the rate of reaction if pressure is lowered. So if you lower the pressure, the rate of reaction decreases because the frequency of collisions decrease, right? The frequency of successful collisions decrease. So in decrease in pressure decreases the rate of reaction. I get 1 mark here. Why? Because the frequency of successful collisions decrease. And again, you'll study this in chapter number 10 again. But successful collisions are those collisions which result in products. So those successful, they are called, so we never really write collisions, we write successful or effective collisions decrease, right? Because effective collisions and successful collisions are the collisions that we really care about, since those collisions result in products. And I think that's it. Yes, the 2024 set is over and it's a piece of cake. You'll study this rate part later on in chapter 10 as well. But the reason why I've added them in this particular chapter is, although I've also had made a video for it, a short video for, the temperatures and the pressures and the industrial process and all of that good stuff. It's largely O-level IGCSE. This is what you need, what you used to write. That's it. Hamza has asked a good question. Sir, do we show this working or directly write it in the table? Hamza, it's good that you directly do not directly write it in the table. It's good that you show working. In A-levels, the more working you're going to show the examiner, the more examiner is going to know that, okay, this guy knows stuff. Please understand that A-level is very conceptual, and the examiner will judge you with everything you write. The examiner is also suspicious, as always, that maybe the student has copied it from somewhere. Where is his working? That's why if you check out the papers checked by the examiners, he even sees all of this stuff, and that further indicates to him that this guy knows his stuff, right? He writes here, what does he write? If you've seen the latest checked papers by the exam, they write seen here. Seen means what? I've viewed it, I've checked it, it's in front of my eyes. He knows this, I've seen this, and I've acknowledged this. So yeah, it's good that you write these things. Done?